So it's my great pleasure to welcome Kennard from Syracuse University, who will speak on torus actions and positive curvature.
Okay, thank you very much for the invitation, and thank you to the organizers for setting this whole thing up. It's really nice to have some semblance of normalcy. And also thanks to the rest of you for tuning in. So this is joint work with Wiemeler and Wilking at Münster. The motivation for the talk comes from positive curvature, so I'm going to start with that. If you're not interested in positive curvature, we'll eventually discuss some things that have nothing to do with curvature. So hopefully some part of this will be interesting. So I'm talking about positive sectional curvature. I'll sometimes abbreviate it like this. Examples are the compact rank 1 symmetric spaces. Beyond these classical examples, there aren't that many examples known. And in fact, there's just a few isolated examples. There's infinitely many, but if you put them into families, there's really not that many. In particular, in dimensions above 24, there are not any. On the other hand, there aren't that many obstructions. So of course, things like positive Ricci curvature or non-negative sectional curvature imply obstructions. But beyond those, in a simply connected case, there are no known obstructions. The most famous one is due to Hopf. Well, it's a conjecture of Hopf that, for example, S2 times S2 does not admit positive sectional curvature. Related to this is to think about the Euler characteristic and whether that's positive in positive sectional curvature. So this is motivated by the Gauss-Bonnet theorem in dimension 2 and the generalized version in other even dimensions. It holds in dimension 4 by the generalized Gauss-Bonnet theorem, or also from classical facts such as the fundamental group being simply connected for an orientable positively curved 4 manifold, classical Singh theorem. But in dimension 6 and greater, it's unknown. So this is an area where there's not much known in general. And so one of the ideas, this is the gross symmetry program, is to study these questions with symmetry. So this is, in retrospect, this is very natural. Everybody adds symmetry to difficult problems to learn something about them. But this was really only formulated, I guess, in the early 90s. So what do we mean by symmetry? This means things like homogeneous spaces and homogeneity 1 manifolds. Those have applications outside of this program. As well as, so you have Lie groups and quotient spaces and these sorts of things. I just want to highlight some of the major successes of this program. So one was that Shankar was a PhD student of Grove, and he resolved a 30-year-old question of turn on the fundamental group. This also led to a new example with positive curvature. So this is a 7 manifold, not previously known to have positive curvature. And this metric was constructed, and the 2 papers were published in 2011. This is the only published example in the last 25 years. So this is not an easy thing to do, but it came out of studying homogeneity 1 manifolds with positive curvature. More recently, Gutta, Karen, and Shankar generalized a construction due to Grove and Ziller, where they showed that, in particular, all exotic 7 spheres admit metrics with non-negative sectional curvature. So this whole Grove program is similar. Same questions, same sorts of questions applying non-negative curvature, and constructions there are not particularly easy either. And so this was a major result. For today, I want to focus on torus symmetry, and moreover focus on even dimensions and on this conjecture of Hopf that the Euler characteristic should be positive. So by torus symmetry, I mean that the isometry group is large enough that its maximal torus, TD, we'll denote it by, has rank that's big. And this is a sense in which I mean big symmetry. So it's bigger than a constant, which depends only on the dimension. So n here is half the dimension. The baseline result of this form, this was the first one of this form in general dimensions, is due to Grove and Searle. They showed that if this constant is half of the dimension, then first of all, they showed that the torus action can't have larger rank. So they call this a maximal symmetry rank theorem. And moreover, if you do have this much torus symmetry, they recovered the diffeomorphism type of the manifold. They show that it's one of these first two manifolds. A while later, Wilking has a paper in 2003 where he basically cuts this symmetry assumption in half. And it's unknown whether you can still recover diffeomorphism rigidity in this case. However, it's significant because he can still recover homotopy rigidity. And he gets a little bit more, but in particular, he shows that the manifold is homotopy equivalent to one of the first three examples. So they're the quaternionic projective space, it turns out, has exactly this much torus symmetry. And so that's added to the list. I'm skipping a bunch of results. I'm just highlighting a few. So here I'm fast forwarding again. This is a result with Manuel Amann. So we were interested in this conjecture in the Euler characteristic, and that's our conclusion. And the point is that we relax the symmetry assumption from something which is linear in n to something which is logarithmic in n. The one annoying thing here is that there's an extra assumption in green. This is that the third Betti number is 0. But that was, as of 2014, that was kind of the best evidence known for this conjecture in the presence of torus symmetry. So the first main result, this is with Wiemeler and Wilking. So this improves this result in 3 ways. So first, the symmetry is cut down a little bit. The B3 assumption is just eliminated. And the estimate on the Euler characteristic is improved to a calculation. What I mean by this is that we compute the Euler characteristic and we show that it's 2, like the case for a sphere, or that it agrees with CPN or HPN, or in dimension 16, the Cayley plane. I should mention that Amann and I had previously done this calculation in dimensions 16 and less, and there we got the same result with these symmetry bounds. So this is new in dimensions bigger than 16. So we were excited about that, but then we have a result we're more excited about, which is this one. So again, we're just being less ambitious with our conclusion, just looking for positive Euler characteristic. And there we can relax the symmetry assumption to a constant. And specifically, the constant is 5. This is exciting because in this area, there are not that many results known where you have a fixed symmetry assumption and arbitrary manifold dimension. I'll mention the only 2 other types of results that I know. So Wrong in 99 proved a result involving odd dimensional positively curved manifolds with circle symmetry. So there in this notation, the constant C is 1, and he has results on the fundamental group. The other class of results of this form are due to Desai and his student, Nikolai Weisskopf. So they study spin manifolds with positive curvature, and they're looking at the elliptic genus, and they prove that certain coefficients of the elliptic genus vanish under these sorts of symmetry assumptions. And there's a family of results, some with circle symmetry, some with T5 symmetry. But again, they're of this type where the manifold's dimension can be arbitrarily large. So I want to go into the tools, and this slide is where I'm going to summarize a bunch of the tools that come in. I'm not going to go into details, but I just want to advertise some of the different things that come in, and then I'll discuss the main tool starting on the next slide, the main new tool. So first of all, we have a torus action, and these things have been studied in general for a long time. And so there's a whole theory of transformation groups. They're going back to Smith theory and then equivariant cohomology. There's conditions relating to Betti numbers, for example, of the manifold to the fixed point sets. And then we combine this with results from positive curvature, and most significantly for a torus action in even dimensions, the torus has to have a fixed point. So that's coming from positive curvature. This goes back to a result of Berger. And in particular, any subgroup of the torus has a fixed point. So inside your manifold, you have lots and lots of fixed point sets. Those fixed point sets are totally geodesic, and therefore they inherit positive curvature. They also inherit torus symmetry, so they look like the same sorts of objects as the ambient manifold. And so it's relevant here. So an important tool here is due to Wilking. And this is in the same paper from 2003. This has been a really significant lemma with lots of applications called the connectedness lemma. So what this does is it relates the topology of the manifold to that of the totally geodesic submanifolds, for example, fixed point components. Related to this is a topological lemma called the periodicity lemma. This says that in this setting where you have all of this stuff, you get a condition on cohomology called periodic cohomology. The next result that's important for this is work from my thesis work. So this was at UPenn working with Wolfgang Ziller. So there we looked at this topological conclusion and just studied that using Steenrod squares and Steenrod powers. And what we did was refined the conclusion of this periodicity lemma. And specifically, it implies that with rational coefficients, the cohomology is 4 periodic. I'm going to mention this a bunch of times without defining it, to my apologies in advance, but all we really need to know is that this implies that the Betti numbers are 4 periodic, all right? And if you think about positive curvature and how that implies that the first Betti number is 0, this implies, therefore, that the 5th Betti number is 0, and then 9th, and so on. So you get half of the Betti numbers vanishing from this condition. To get the other half, you need to know that the 3rd Betti number is 0. And this is the first new tool. This was something that I personally had been trying to figure out for a long time. So this is a new lemma that, unfortunately, I don't have time to discuss, but it involves some new ideas involving using equivariant cohomology. It requires that you look at all of the fixed point components at once and think about how all of those Betti numbers add up and everything's 4 periodic, and can this happen? And well, the point is, under the sorts of conditions that we have for all of this other stuff to apply, we can prove that the 3rd Betti number is 0. So again, I'm not sketching the proof here, but hopefully it's believable that if you can show odd Betti numbers are 0, that's a good thing for showing the Euler characteristic is 0. So again, these are kind of the tools that come into this, and you mix them up and you put them in the oven. And the upshot of all of this is that to prove the main theorem on the Euler characteristic, it suffices to look at one fixed point component at a time, this F right here. And it suffices to find 3 subgroups, H, H1, and H2, so that this technical green condition holds. That's for the B3 lemma. I'm not going to discuss that ever again. And then the main thing is that the fixed point components, N of H and N1 and N2 of H1 and H2, have the property that these submanifolds intersect transversely in N. In other words, at points where they intersect, their tangent spaces span the whole tangent space of N. All right, so that's the important condition we need. And this gets to the next point. So we need to find transverse intersections. And how do we do this? And again, this is the main point here. This is, you can forget everything and just say, okay, we want to find transverse intersections. So the way you do this, oh yeah.
Would you mind going back again to that after baking? There. Yeah, so what is H, the isotropy group?
Okay, so H, Yeah, you can think of it that way. So you can also just think of H as being a subgroup, and it's a subgroup of TD, so its fixed point set N contains the fixed point set of TD.
All right, thanks.
Okay, hope that helps. Yeah, so the way we do this is to linearize the problem by moving to a point in the fixed point set, or in that fixed point component, and studying the isotropy representation. So here V is the normal space to F at P. And to translate the problem, it just means that, again, we have a representation of TD, and we want to find subgroups, and their fixed point sets are denoted in this way. So this is the representation, so everything's linear. These are subspaces. And the condition of transversality is just simply that these subspaces together span the whole subspace. This is the fixed point set of H. So first of all, this is kind of old news, this whole strategy, and I just want to mention something for context. For the results with logarithmic symmetry, we can do this. We can find these subgroups by looking among subgroups of involutions. This idea goes back to that 2003 paper of Wilking. Involutions are really easy to work with. You know, if you multiply two of them, it's very easy to see what happens at the level of the isotropy representation. And it turns out that log of n base 2, or I might be off by, yeah, something like log of n base 2, that's the critical value where looking at subgroups of involutions is enough. You need at least that much. So, you know, it simplifies our lives to look at involutions, but on the other hand, you're missing out on a lot of other possible subgroups. And this gets to the main new lemma. So this is the main way we get transverse intersections with a lot less symmetry. So here's the theorem. We call this the S1 splitting theorem.
Can I ask a question too?
Yeah.
You require that Hi mod H are circles, right?
Right.
So what are the cyclic subgroups, or the Z2 to the D subgroups? They're not the HIs.
Okay. So in that previous, so I'll go back just quickly here. Yeah. So this condition in green is required for the B3 lemma, and in the previous work there we didn't have the B3 lemma, so actually we didn't need this extra condition. We got so the HIs were allowed to be finite subgroups in that case.
So that's because you couldn't prove separately that B3 is 0.
Right, right.
So from now on, all the HIs and H's are finite subgroups.
Well, with this new stuff, we're going to take more interesting subgroups. Yeah, but yeah, previously they were allowed to be finite subgroups.
Thanks.
Okay, thank you for your question. Okay, so this is the main new theorem, and now, so the point is there exists this subgroup H that we want, and the statement is that, so VH is a fixed point set of H. The statement is that if you can choose a subgroup, and now for clarity, this is going to be a one-dimensional subgroup. So a circle, or in general, a disconnected one-dimensional subgroup. And the statement is that in that fixed point set, the induced torus action, so this now has dimension d-1, so the torus splits as a product. Of course, that's true abstractly. The vector space splits as a sum. But moreover, you can do this in such a way that the circle only acts on V1 and the leftover torus only acts on V2. So in the matrix representation for this, that the whole thing is a block diagonal representation where the circle only acts here and the rest of the torus only acts here. So in particular, if you look at the fixed point set of the circle, since it only acts on V1, it fixes all of V2. And similarly, this fixed point set fixes all of V1. So when you take the span of those two fixed point sets together, you get the whole thing. That's what it means to intersect transversely. So you get transverse intersections from this already with the T3 representation. So why is T5 needed? This has to do with a lie that I told on my previous slide. This was advice I got as a grad student from my advisor that I should lie at certain times in talks. I didn't mention this condition, but there's an extra condition involving the dimensions of the fixed point sets that has to hold. And it turns out that we can satisfy this extra condition for T5 actions. The point here is that if you have a T5, then your leftover torus is a T3, and you can apply the splitting theorem again to get more splittings, more transverse intersections, and it takes some work, but you can show that you can satisfy this other condition. So again, this is kind of the main new technical tool, and it's just a statement about torus representations. I want to spend the next few slides just talking about this. So here's a theorem again in abbreviated form. Here's an example. So this is, I'm switching to the unitary group for simplicity. This is a representation of T3. And the subgroup you can choose is this circle subgroup, this quasi-diagonal circle inside the T3. And it's easy to see that this acts non-trivially on all of these directions except for the purple directions. And so the fixed point set is just two-dimensional. The induced action you can check is still a T2, so this must split as a product of circle actions on a two-dimensional complex vector space. Quickly, I wanted to point out that, a simpler attempt would be to take H to be, for example, the first circle factor. It's the first thing you try maybe, but you can see that that doesn't work because the fact that Z1, Z2, and Z3 are all tangled together means you have to be a little more clever with your choice. Here's a more complicated example. I switch notation so it fits on the slide. Here, the interesting thing I think is that you cannot choose a connected subgroup H. You cannot choose a circle here. This is an example where you have to choose a disconnected subgroup. There's just too many representations. And this, I want to illustrate with this example a different point. So I want to look at this subgroup first. This is a finite subgroup. This is not going to be our H, but this is going to be an intermediate step. So take this involution and look at the fixed point set of it. You can see that it's precisely these purple directions which are fixed. So the fixed point set is like this. Now, the leftover action, or the induced action, just has kernel equal to this. That's easy to see. And so what the point is, you still have a T3 action, but it's on a smaller dimensional vector space. So in terms of finding your one-dimensional subgroup, you've made your problem easier. All right, and specifically, if you use this circle, and then you put it all together to get a subgroup of the torus, this is the one-dimensional subgroup, which gives you a splitting. And in fact, it's you don't have to do any computation. You can just see that the fixed point set is, again, just two-dimensional, so it must split. So this point in example 2 illustrates this point that if you're trying to prove the splitting theorem, it's really easy if there's a finite isotropy group. So this Z2 is precisely the isotropy group if you take the directions, a vector involving all three of these directions. And use the same idea in general. You look at the fixed point set of that finite group, you look at the induced action, which is a torus of the same size, and then by induction, you're done. So this is the easy case. It turns out, moreover, that if you have a disconnected isotropy group, such as this, that it's a straightforward lemma that if you have a disconnected isotropy group, then you also have a finite isotropy group. So just like in this example. So the point of this slide is that you can assume that all isotropy groups are connected. And this turned out to be a really strong property. I want to discuss this property a little bit. So now I just want to play with this property. We have a torus representation with connected isotropy groups. And more specifically, this means that all isotropy groups are connected. To show you a little bit why you might expect this to be a very strong condition, here's a very easy representation that's just loaded with disconnected isotropy. So for example, if you take the second direction and you ask which group elements fix E2, well, it's easy to see that, you know, the cube roots of unity in the first factor fix it, but also Z2 and Z3. So there you go. You have a disconnected isotropy group. If you take the red directions, what you do is you intersect these kernels, and you solve those equations, and you get a Z2, and then I guess in this case the Z1 could be anything. So again, a disconnected isotropy group. And the third one, this one might be a little bit better hidden, but if you look at these three subrepresentations and you take a vector such as E4 plus E5 plus E6, then to fix that vector, it's equivalent to solving these equations, and you still get a Z2. So -1, -1, -1 is the only non-trivial element that fixes those vectors. There's many other types of ways you can get disconnected isotropy groups. For example, you might call this a 3-cycle. You could write down a 5-cycle, or other lots of other ways to get finite isotropy groups or disconnected isotropy. The reason I put these examples is that actually these are somehow the only three you really need to understand for the proof of the splitting theorem. Not that I'm going to get to that in the next 25 minutes or so, but it's kind of surprising that you somehow, just by studying T3 representations, you can somehow already know everything you need to know. So these things are rare. You should think of this as a very strong condition. To give you, I want to next give you an example of, so these things do exist, of course. Here's an example for T4, and I'm writing it inside the unitary group, again, for notational reasons. So this is a lot of representations, but here I'm just taking Zi, and over here I'm taking all Zi, Zj, where I is less than j, and where I'm putting a conjugate on the second piece. You have to be careful with the conjugates, as this example shows back here. But it turns out you can work out the equations. All isotropy groups here are just circles, T2s, T3s, and connected subgroups. Here's a different example. What you do is you copy and paste the blue representations here, and then you add this one. So there's 9 different representations here, irreducible representations. And it turns out that these are different in the sense that you cannot put this inside this representation. This is not a sub-representation. These also have a nice property that they're maximal. What I mean there is if you try to add a representation here or add a representation here, then unless you're adding multiplicities, repeated representations, except for that kind of trivial issue. If you try to add something else, then you necessarily introduce disconnected isotropic groups. And this is a classification statement that actually, if you look at representations which are maximal in this sense, and which also don't have any repeated representations, because that's kind of a trivial thing, then it turns out these are the only 2 maximal T4 representations with connected isotropy groups. For T3, there's just one. It's the natural subrepresentation of this one. For T4, there's 2. For T5, we've also done this, and there's 4 different representations. But that's it. This is a really strong property. I should mention we don't use this classification. We don't use this much information for the T5 theorem. We just use the S1 splitting, but it's kind of natural to try to understand what these look like. Okay, I want to spend a few minutes about on the proof of this. So we have a torus representation with connected isotropy groups. What we do is we look at the weights of this representation. These are, like in the previous examples, excuse me, these are the integer exponents of Z1, Z2, Z3. So we take these, we write these as column vectors, so integer entry column vectors, and we build a matrix where we put all of them together. So this will be a matrix with D rows and K columns, where K is the number of irreducible subrepresentations. The main lemma here translates this geometric condition about connected isotropy groups into something elementary about determinants. The statement is that you have this matrix, and every submatrix of full rank has determinant plus or minus 1. So every D by D submatrix could have determinant 0 or plus or minus 1. All right, to give you an example here to illustrate what I'm talking about, here's a T2 representation. And I've built this weight matrix. So it has 2 rows because there's two variables, Z and W. And you can see I'm just taking the integer powers. For example, this is Z to the -1, W to the 1. That's that entry, that column. And this submatrix I've highlighted in red clearly has determinant 2. And that's related precisely to the fact that if you look at the isotropy group for those directions in the isotropy, or in the representation, that involves intersecting these kernels, and you get an order 2 group. So order 2, determinant 2, those are, in general, that's the statement that if you have a determinant larger than 1, then you get a finite isotropy group of order larger than 1. So that's a very easy example. To continue the analysis, what we do is you can always assume that the weights include the standard basis vectors. This is just obtained by precomposing with an automorphism of the torus. You're just changing the basis. And now what this means is that, imagine a D by D submatrix where you take D minus 1 of the standard vectors, and then you just take 1 of the other weights. That determinant, that D by D determinant, is just going to pick out one of the entries of the weight that you picked. And since the determinant is 0, 1, or -1, this means that your weights are just made up of elements from -1, 0, and 1. So they come from this tiny finite subset of all possible weights. And in particular, this obviously implies that the number of different weights is at most 3 to the D. It's inside this finite set. And this bound is independent of the dimension of your representation. You see, it only depends on the dimension of the torus. If you analyze this further, we prove that in fact you can improve this upper bound to this number. You might recognize this as D plus D choose 2. That's precisely the number of representations you have in the example on the previous slide. I don't want to make everybody dizzy, but if you go back to the previous slide, there was T4 representation with 10 representations. So it turns out that's the maximum number possible. That example generalizes to all cases, and you get that this is sharp. In fact, we also prove that that's the only representation with this maximal number of irreducible subrepresentations. So again, this is not a result that's used for the splitting theorem, and it's not used for the T5 theorem, but it's kind of easy to digest, and it's a result which is independent of the vector space dimension. Remember, in the geometry problem, the vector space is basically the tangent space of the manifold. So this is a statement about the isotropy representation, which is independent of the manifold dimension. You might start to believe now that we can prove something which is independent of the manifold dimension. So specifically for the splitting, there's a more technical statement. It again has the flavor that there are not that many weights. It says that you can find an affine subspace, all right, of codimension 2, such that there's only one weight in this affine subspace. All right, so a little more technical to digest, but if you're willing to believe this statement, it's pretty easy to prove the rest of the splitting theorem. For example, how do you get your one-dimensional subgroup? Well, you take these D minus 1 weights, that gives you d minus 1 of the representations. You intersect those d minus 1 kernels, and you get a one-dimensional subgroup. That's the H which works. All right. To get your circle and your leftover torus, you intersect these kernels and those kernels, and then, or yeah, I mean, you can write the rest of the proof now. It's not too hard. Let me see on time. I had a couple of examples. So here's this example again. You know, E1 is the weight here. E2 minus E3 is this weight, and this one is this weight. And anyway, this is an easy illustration that this second condition is true for this example. And if you intersect those kernels, this is the H, which gives you the splitting. And there's some details. I had a second example, which I need to skip because of time. I'm happy to share these slides, by the way. I want to keep moving. So I do want to go back to the geometry now. That's all I want to say in general about the torus representations. So with T5 symmetry, remember we're studying one fixed point component at a time. We look at the isotropy representation. And with T5, you apply the splitting theorem twice. And again, I'm abbreviating the discussion quite a bit here, but when you apply it twice, you get a two-dimensional subgroup, and you have split off two circles, and you have one left over. So you have three circles and three different fixed point components, denoted by these things. And any two of them intersect transversely with another one. So you see now you have some choices with which transverse intersection to deal with. Yeah, it takes actually a little bit of work, but we proved that this is enough to plug into the connectedness lemma and the periodicity theorems, and also the B3 lemma. And in particular, the odd Betti numbers vanish, and in fact, what for periodicity really implies is this, that this fixed point component of H, this two-dimensional subgroup, is just one of these four manifolds. This notation is very concise, and so I love it, but what it means is the rational cohomology ring agrees with these spaces. This is a space that shows up, which somehow shouldn't, so I put it in red, but it's okay. What you can do using basic results from equivariant cohomology is you can push this information on Betti numbers down to the fixed point set. That's the easy direction to push this information. And it turns out that the fixed point components are one of these things. And by the way, the reason this comes up is for the same reason that if you have a circle action on HPN, the fixed point components look like HPN or CPN. Same thing here. So this is a statement. What this tells you is that the fixed point components look like they do for linear actions on these model spaces. As it turns out, though, S2 times CP does not have periodic cohomology. It's again, I'm not defining it, but it just doesn't. And so it turns out you can rule this out easily by sort of writing these arguments in a different order. But S2 times HP is still there. And actually, we can rule this out too. This is not easy. This involves much more analysis of the fixed point components. And not just one at a time now, but looking at all of them together. It's important that we relate the isotropy weights at F to the other fixed point components. There's ways to do this. Moreover, for this, we also use the splitting theorem again. So if you think about what the splitting theorem says, is that if you restrict the action to N, there you have a T3 action left over, which splits as a product of circle actions. What this means is that the isotropy weights at F are very easy. There's just three of them, all right, with multiplicities. So the point is, like, the circle splitting simplifies the information on the isotropy weights, and we relate those to the isotropy weights elsewhere. And again, this is not something I can summarize in a minute or two, but the point is we can roll that out. And this gives us this theorem. This is really the main theorem for T5 symmetry that we have. It says that all of the fixed point components are one of these three model spaces. at least at the level of rational cohomology. That's what I mean here, rational cohomology. Now, you might not care too much. I want to motivate why you might care about the fixed point components. After all, you're starting with a Riemannian manifold, and the conclusion is about these fixed point components. You know, what does this mean about the manifold itself? Well, what I want to do is state a different theorem that assumes something about the fixed point components. And specifically, I want to study a bigger torus action, a T8 action. And I want to make the assumption, which is the same as the conclusion of this theorem. So I'm going to assume that subtori of rank at least 5 have standard fixed point components. So I mean rational cohomology, spheres, CPs, or HPs. Then under an extra condition called equivariantly formal, we can, this is a strong condition, this allows us to lift this information on rational cohomology up to the manifold itself. So I want to, first, what does equivariantly formal mean? It means that when you build the Borel construction of this torus action, also known as a homotopy quotient, there's a projection down to the classifying space of T, and this is a fibration with fiber M. You look at the spectral sequence, and the statement of equivariantly formal is equivalent to saying all differentials in that spectral sequence vanish. If you've read about equivariant cohomology, you know that this is the easiest case where everything's really easy and nice. You also learn this is a very strong assumption. But anyway, so to move on, this is a partial converse to results of Smith and Braidon. So one of the classical Smith theorems is that if you have a rational cohomology sphere and a torus action, the fixed point set is again a rational sphere. And more generally, Braidon has a result that if you have a rational cohomology sphere, CP or HB, then every fixed point component is again one of those 3 types. You see, we're kind of doing the opposite. We're assuming that all the fixed point components are standard, and we're showing that the manifold is standard. Regarding this equivariantly formal condition, I want to point out that spheres, CPs, and HPs have vanishing odd Betti numbers. And that's one of the sufficient conditions for any torus action to be equivariantly formal. So in a sense, you know, in these theorems, you don't have to assume equivariantly formal, but it's automatic. So I think it's fair to call this at least a partial converse to these results. I also want to mention that Theorem 2 includes the special case of GKM actions. These are extremal actions in a sense. These are where the fixed point set is as small as possible. And moreover, the codimension 1 subtori also have fixed point sets of as small as possible. So they're just S2s. And there's a result using positive curvature by Gurchis and Wiemeler recently, where they studied GKM and similar conditions in positive curvature. And a lot of their work is topological. So even though Theorem 2 does not involve curvature, we can use a lot of the ideas from that paper. It ends up being closely related. So the corollary of these 2 theorems together is this. So we put back in positive curvature. We assume T8 symmetry. And I'm going to just assume this condition I mentioned earlier, that the odd Betti numbers vanish. Everybody knows what that means. So assume the odd Betti numbers vanish. What does this mean? Well, for Theorem 2, that means that the action is equivariantly formal. And, you know, is it true, this condition on T5 subtori, that the fixed point components are standard? Well, yes, by Theorem 1, T5 fixed point components are standard in positive curvature. So if you combine these, you see that T8 symmetry, positive curvature, and vanishing odd Betti numbers are enough to conclude the rational cohomology of the manifold. And it's, again, one of these standard types. We think this is the best evidence yet that it's you know, hard to produce positively curved metrics with any symmetry. In large dimensions, T8 symmetry doesn't seem like that much. But nevertheless, assuming this green condition, you only get the rational crosses. and well, these three rational types. Okay, so I put this condition in green because it reminds me of the B3 equals 0 assumption from long ago. Maybe this is not needed. So this is related to some ongoing work, but I want to mention that maybe this condition is natural, and here's why. So the T5 theorem implies positive Euler characteristic. And another well-known conjecture in this field is the ellipticity conjecture due to Backrove and Halperin. And that conjecture applies to positive curvature, and it implies that the manifold should be rationally elliptic. For positive Euler characteristic, all I'm going to draw from that is that it means that the odd Betti numbers should vanish. So assuming this conjecture, combined with the T5 theorem, this green assumption is automatic. So it's at least believed that that's a natural assumption. On the other hand, some ongoing work is related to this theorem. So we've proved this, but we're trying to optimize the precise statement. But what we do is we say, let's forget about this green topological assumption, and let's add this blue geometric assumption on the action. In other words, suppose you have positively curved manifold with a torus action, and suppose that its isotropic groups are connected. And this is kind of still too strong, but basically assume all isotropic groups are connected. You really only need this in a neighborhood of the fixed point set. But anyway, there's some D, there's some fixed dimension D. It's larger than T8, but there's some fixed D where we can conclude, again, the rational cohomology of the manifold. So that's another result. Yeah, so the other question we're interested in, and this we're just stuck on, but I'll give you the background. So it would be nice to prove more than just rational cohomology. And one thing that seems plausible is to prove Z2 cohomology. So in all of these statements where we conclude that such and such is a rational cohomology so-and-so, we would like to say a Z2 cohomology. So for this, we would need to remember where we get the rational cohomology, and that's from the four periodicity theorem. That theorem is for rational coefficients. So to answer this question, we would have to get a Z2 cohomology statement telling us four periodic. And this goes back to a question I posed in my thesis work. So that if you study this condition of periodic cohomology with Z2, then I expect that this should imply four periodic Z2 cohomology. Some evidence for this is that, one of the main lemmas, the main lemma in proving the rational four periodicity theorem actually involves Z2 cohomology. And specifically, it's that if you have any period whatsoever, and you take the minimum period, that minimum period has to be a power of 2. This is a direct generalization of a result of Adam. This is as in the Adam relations for Steenrod squares. That's where the proof comes from. So that's some evidence, but there's lots of powers of 2 beyond 1, 2, and 4. A further piece of evidence, though, is that if K, which is the period, divides the dimension, it turns out you can show that all of the groups that are not divisible by K vanish. So H1, H2, H3 are 0 up until HK. But then what happens is you have a single generator in degree K, and powers of it generate the rest, just like CPN and HPN, except now K can be anything. Well, except now Adams proved that actually K can just be 1, 2, or 4. So if you like, this is a special case of this conjecture where K divides a dimension. There's various other special cases we know about where the conjecture is true. but I want to advertise this conjecture as widely as possible in case somebody who's more competent with these tools could prove it. It would have applications to this area. Okay, so that's it. I'm going to put up my references. Thank you all for attending, and thanks again to the organizers for making this happen.
Thank you, Lee, for a wonderful talk. Are there questions?
Can you go back to the baking the oven slide?
Yeah. Yes. Dun, 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 dun. This one here?
Yes. The first question is, how long do you have to bake the oven? How hard is it?
Well, with all these ingredients, it's not terribly hard. Well, let me put it this way: if you assume T7, it's really pretty quick.
So what's the relationship? What do these fixed point sets imply?
Sure. So what happens is N1 and N2 intersect transversely in N. So they're also totally geodesic because they're fixed point sets. So you apply the connectedness lemma. The connectedness lemma tells you that the inclusion map from N1, so let's just say N1. Okay, I'm going to lie a little bit, so if Burkhard and Mikkel are watching, just ignore me for a minute. Basically, you get that the inclusion maps are highly connected maps, so they induce isomorphisms on homology and cohomology. You apply Poincare duality and combine that condition, that gives you the periodicity lemma. This says that the cohomology of N is K-periodic, where K is the codimension of one of these submanifolds. The rational four periodicity theorem says, given K-periodic cohomology, you conclude four periodic rational cohomology for N. Given that, with the B3 lemma, you know that now that the first and the third Betti numbers of N are 0. So the B3 lemma applies to N, not to the whole manifold. But N has B1 and B3 equal to 0. So then with four periodic Betti numbers, all of the odd Betti numbers are 0. And at this point, the quickest way to positive Euler characteristic is to apply a result from equivariant cohomology that says the odd Betti numbers of F are smaller than or equal to the odd Betti numbers of N. So if the odd Betti numbers of N are 0, then that's true for F as well. So F has vanishing odd Betti numbers.